Assalamualaikum. This is your Thermodynamics 2 class, and today is lecture number 22. So can anyone confirm what's appearing on screen right now?
So we have seen the slide lecture 22, chapter 15, chemical reactions.
Thank you so much. Okay, so as it is mentioned that, before starting the lecture, as communicated with CR, your quiz has been postponed until tomorrow. Okay, so make sure you can attend the quiz. The timing is the same, so it will open at 10 a.m. in the morning and close in the 6 p.m. at the evening. Okay, so the quiz date is 5. So you have to just follow the time and the course is the same, which we already discussed in the previous class. Okay, so here coming towards the lecture number 22. Okay, so as it is mentioned, chapter 15 and chapter 17. So first we will discuss some problem related to chapter 15, which is the chemical reaction, and then we will move towards the new chapter, which is the compressible flow, and we will discuss why we are going to study compressible flow in the thermodynamics, and because it is a fluid mechanics topic, but we still have to look into compressible flow in the thermodynamics as well. Okay, so coming towards the first part, which is this question we already practiced in the previous class, so, and this is the question which we have to look into today lecture. So calculate the lower and higher heating value per kg of mixture at 25 degrees Celsius for the stoichiometric mixture, air and benzene vapor. Given that enthalpy of combustion at 25 degrees Celsius of benzene is equal to minus 3169500 kilojoule per mole. Okay, so this is the question. You have to note it down the data, and then we will see that how to solve this question. So starting from the solution, again we have to start from the combustion equation. So the combustion equation is C6H6. Make sure it is gaseous and 7.5. So this equation I will provide with the problem statement. So don't worry how to develop this equation. Okay, so this is the chemical equation. Okay, so from here, our required thing is to find the lower heating value of mixture and the higher heating value of the mixture. Okay, so these things we have to find by using this chemical equation. Okay, so first thing, if you can recall the previous lecture, I already told you that how we judge that the value is lower heating value and either it will be the higher heating value. That depends upon the H2O, which come in the product side, okay, during the chemical process, and that will be decided by the phase. Okay, so if it is the gaseous phase, the H2O, it means we have the lower heating value, and if it is in the vapor phase, it means we have the higher heating value. Okay, so this is the main point over there. So enthalpy of combustion is mentioned in your problem statement of C6H6. and it is in kilojoule per kilomole, which is minus 3169500 kilojoule per mole. Okay, so here, if you recall again, the heating value, lower heating value is basically, or higher heating value is the absolute value of enthalpy of combustion. Okay, so here it is mentioned that H2O is in the gaseous form. So if you can just look in the chemical equation, so it means this enthalpy of combustion is equal to lower heating value. Okay, and it is the absolute value, so 3169500 kilojoule per mole is the lower heating value in kilojoule per kilogram per mole. Okay, so now here we have to find lower heating value per kg of mixture. Okay, in kilojoule per kg. Okay, so what you have to do is lower heating value, and you can say for the mixture is equal to 3169500 divided by number of mole of mixture, molar mass of mixture. Okay, so where you have to get the number of mole of mixture, and mixture mean fuel plus air. Okay, so this is our mixture. Okay, and so number of mole you have to calculate it, okay, by using directly from the chemical equation. Okay, so here it is mentioned all the number of mole, and molar mass you can calculate using the thermodynamic table, or either you have already remembered that what is the molar mass of C6H6, O2 and N2. Okay, so you just have to plug the value and you will get. Okay, so I am directly going to write, so you have to calculate it by yourself. So the end result is 78 plus 240 plus 790. So simply I have just divided number of mole of mixture divided by molar mass of mixture. And here it is C6H6. This is O2, 7.5 into O2, and this is 7.5 into 79 by 21 into N2, which is 28 molar mass. Okay, so do not confuse this time. So here we have the value, which is 2861 kilojoule per kg. So now here we have to find the higher heating value also. Okay, so higher heating value basically lower heating value plus mass into heat of vaporization, latent heat of vaporization, HFG. Okay, so lower heating value you can easily get from this. Okay, so 3169500 plus mass of H2O in the product side, so 3 into H2O you have to just calculate the molar mass, so which is Ke into latent heat of vaporization. You can easily go to thermodynamic table and find the value, which is 244, and you will get the value, which is 3301368 kilojoule per mole. Okay, so again it is in kilojoule per mole, so we have to find the heating value for the mixture in kilojoule per kg. Okay, so same procedure, you have to divide this term 3301368 by divided by number of mole of the mixture and molar mass of the mixture, and you will get the required answer, which is equal to. So I am just going to write in this area. So higher heating value of the mixture is equal to 2980 kilojoule per kg. Okay, so the number of mole and molar mass of the mixture you have to divide by yourself, and you will get the final answer. Okay, so this is the procedure which we have to follow for this type of question. So you have to note it down, and then we'll move towards the next topic, which is compressible flows. Okay, so your chapter number 15 is completed at this point. Okay, so you have to go through and practice the problems related to the topic which we already discussed. Okay, from the end of this book chapter. Okay, so if we have some spare time at the end of the semester, so we will surely try some more questions. Okay, so I hope you have some understanding, develop some understanding based on chemical reaction related to combustion processes. So coming towards the next topic, which is the compressible flow. So I had mentioned that over there, uh, and I believe that you already know what is the compressible flow and incompressible flow. So the difference is that in compressible flow, we have to say that there will be change in density. Okay, and in the incompressible flow, we assume that there is no change in density of the fluid. However, in our daily life, all the flows which we are talking about are the compressible flows. So only it is our assumption, and try to simplify our problems. So that's why we assume that the flow is incompressible. Okay. However, there is no flow which is called as a incompressible flow. Okay, so now here the main point is that why we are going to study compressible flow in the thermodynamics as it is fluid mechanics to me. Basically, if, for example, if I can say you have to perform the thermodynamic analysis of high-speed moving object, for example, aeroplanes or there will be fighter jet or some sort of helicopter, okay, or any type of thing, okay, where there will be high speeds involved. So then we cannot solve it with the assumption that the flows are incompressible because there is a high speed, and then the compressibility effects are the main important factor, and these compressibility effects also affect your thermodynamic analysis. Okay, so that's why we have to look into that how to deal with the compressible flow and relate it with the thermodynamics. Okay, so we will look into some introduction part first, and then we will come towards some idea related to the compressible flows. So compressible flow is that flow in which density of the fluid changes during flow. So all real fluids are compressible to some extent, and therefore their density will change with change in pressure or temperature. So if the relative change in density is small, the fluid can be treated as incompressible flow. So this is the condition by which we can decide that we are going to assume that incompressible flow, that if the relative change in density is very small. A compressible fluid such as air can be considered as incompressible with constant density if changes in elevation are small, acceleration is small, and temperature changes are negligible. So this is the condition from where we have to assume that the air is incompressible. However, air is a compressible fluid. The gases are treated as compressible fluids, and study of this type of flow is often referred to as a gas dynamics. Okay, so some important problem where the compressibility effect has to be considered are flow of gases through nozzle and orifice, compressors, flight of aeroplanes, projectile moving at higher altitude, and water hammers. Okay, so these are some basic area where we have to consider the compressibility effect. So based on thermodynamic, if you can notice that we have to deal with the nozzles, and there are compressor of steam power plant. So where we have to consider these compressibility effect, and these compressibility effect plays important role, and these affects the drag coefficient of the bodies by formation of shock waves, discharge coefficient of measuring devices such as orifice meter, pitot tube, stagnation pressure, and flow in the converging and diverging section. Okay, so these all topics we will discuss in detail. Okay, the shock waves and all the things. Okay, so here the basic significance of the compressible flow comes from that why we are going to study compressible flow in the thermodynamics. Okay, so how we can judge that the flow is compressible flow and incompressible flow? So this can be judged by using one dimensionless number, which is the Mach number. Okay, I hope you already have some idea what is the Mach number. So Mach number is measure of importance of density change for compressible fluid, and it is basically the ratio of your velocity of fluid to velocity of sound, and we denote it with this Ma, which is the Mach number, or we can say Nma, small m. And just a rule of thumb that if the Mach number is less than 0.3, we assume the condition for the incompressible flow, and if it is greater than 0.3, then it is a compressible flow. Okay, so here we can just take one example. So for example, if I can say that there is one aircraft that is flying at some altitude, and the temperature and the velocity of that aircraft is, for example, 350 meter per second. Okay, so here we have the local velocity is known to us, and now we have to calculate the velocity of sound at that specific altitude. Okay, because if it is at altitude, so it means the temperature is changing. Okay, so the temperature is lower at the higher altitude. Okay, so that's why we have to find the velocity of sound at that elevation and at that temperature. Okay, so then we will get the velocity of sound also. Okay, and if we can divide these two parameters, we get the Mach number, and then we can say that our flow is incompressible or compressible. Okay, so this is the main point where we can judge. Okay, and other important point is that density changes is not significant, so which is less than 10%. Still, we can assume that it is the incompressible flow. Okay, if the density changes is less than 10%. So here, compressible flow, the Mach number we already discussed. So it is ratio of local velocity to speed of sound, and speed of sound we have to denote with the c. Okay, and if the Mach number is less than 0.3, we assume it is the incompressible flow. Density changes are negligible. If it is in between 0.3 to 0.9, so we define it as a subsonic flow. So density effects are important, but shock wave do not develop. So this we will discuss at how the shock waves are developed during the compressible flow in the coming lectures. Okay, then if the Mach number is in between 0.9 to 1.1, so it means we have the transonic flow, and shock wave appear and divide the flow field into subsonic and supersonic region. Similarly, if Mach number is in between 1.1 and 5.0, so it is the supersonic flow. So shock wave are present and there are no subsonic region over there. And if the Mach number is greater than 5.0, so then it is the hypersonic flow, and very strong shock waves and property changes we have seen in this type of flow. And these all flows are the basically characterization of compressible flow: subsonic, transonic, supersonic, and hypersonic flow. Okay, so this is the basic idea behind the incompressible and compressible flow, how we have to characterize the compressible flows. So before starting towards the main topic related to the compressible flow, we just have to look into some basic equation and revise it, okay, so that you are not confused when we have to use these equations. So you already know ideal gas equation: P is equal to rho RT, and then R is the gas constant over there. So then if you have to define the specific volume, so specific volume is basically 1 over rho, and ideal gas equation become P specific volume is equal to RT. And then for an ideal gas, the internal energy is a function of temperature only. So ideal gas specific heat at constant volume is defined as Cv du by dt. Because these relations you already seen in the previous lectures as well. These are not a new one. Cv is also a function of temperature, but for moderate temperature changes, it can be taken as constant. So then we already look in the gas power cycle one relation, which is delta U is equal to Cv delta T. Okay, so this is also the basic equation, how to relate change in internal energy with the Cv and change in temperature. Then enthalpy is defined as U plus RT. Okay, so this equation also we are familiar with. And then for ideal gas, enthalpy is also a function of temperature only. So ideal gas specific heat at constant pressure is defined as Cp dH by dt, and Cp will also taken as constant in this course, okay, or in this lecture of the compressible flow. So we just consider that air, so air Cp and Cv are known to us. For constant Cp, change in enthalpy is delta H is equal to Cp delta T, And then also this is the equation we didn't use in the previous lecture, which is Cp minus Cv is equal to R, okay, which is the gas constant R. Okay, so the proof is very simple. So we will see in the coming slide that how to prove that Cp minus Cv is equal to R. Okay, so this is the equation we also use frequently in this lecture, which is the compressible flows. And then specific heat ratio, K, is basically the ratio of Cp by Cv, and Cp is related with the there is another term by which we get by combining two relations, which is this and this. So simply you have to put these value of Cp from this equation to, you can say this equation 1 and equation 2, and you will get one relation R into specific heat ratio divided by specific heat ratio minus 1, and then Cv is equal to gas constant over specific heat ratio minus 1. So these are some simple relations which we will see in this lecture. Okay, and then change in entropy. Also, I think you already know from chapter number 7 of your Thermodynamics 1. So delta S is related with temperature and density and with the pressure by using these equations. And then for an adiabatic, no heat transfer and frictionless flow, which is known as isotropic flow, entropy remains constant. And then there will be one familiar term, which is speed of sound. How we have to find the speed of sound? This is by using this relation for the isotropic flows. So isotropic flows under root K R T. So K is specific heat ratio, R is the gas constant, T is the temperature in this relation. So first we will just look for the value of how this Cp minus Cv come from. So Cp minus Cv is equal to R. Okay, so this relation basically come from the basic equation of enthalpy is equal to internal energy plus PV, and if you can just put the value of PV, which is equal to mRT, and if you can just differentiate both of these sides, so you will get the value this dH is equal to du plus mR d t. And if you put the value of dH in this equation, so m Cp dt is equal to du value is m Cv dt and plus mR dt. So from here you can easily eliminate delta t, and you can also eliminate mass. So our equation becomes Cp is equal to Cv plus R, and Cp minus Cv is equal to R. Okay, and similarly, if you put the value of specific heat ratio, so for example, if I can put the value of Cp, so which is Cp is equal to K into Cv in this equation. Okay, so I will get one relation which is Cp is equal to R by K minus 1, and simply if I can put the value of Cv from the same relation, so I will get the value of, so this is the value of Cv and this is the Cp value, this Kr divided by K minus 1. Okay, so these are some relations which we have to use. Okay, so now coming towards the important point over there, that we have to know that how we have developed this relation for the isotropic flow for the speed of sound. Okay, so let's prove this equation first, so that we will get some idea. Okay, so in order to prove this equation, first thing is you have to assume some system. Okay, so here we have to assume that there is a piston cylinder arrangement. Okay, so for example, I can say this is the piston cylinder arrangement, and here is the piston. And the length of this cylinder is L, and there is some fluid inside this piston cylinder arrangement. Okay, so here our main target is to develop the equation which is C is equal to under root K R T. Okay, so here we are talking about the speed of sound. So first thing you have to know that what is the speed of what is the sound? Okay, basically sound is a form of wave. Okay, because for example, if I am talking to you and you are listening, so it's mean I am communicating with the help of some waves. Okay, so that waves will just transfer whatever the voice coming from my side to your side. Okay, so these are called the pressure wave, and the sound wave basically these are categorized as a weak wave. Okay, so why we are called as a weak wave? Because if I am talking to you and this is the sound wave, and these sound wave do not result in the burst of your eardrums. Okay, so it's mean that this is the weak wave because it will not cause any damage to your eardrum. However, in a similar way, if I am talking and your it will result in the uh, damage of your eardrum. Okay, so this is called the shock wave. Okay, so this is how we can just simply say that how we denote with the weak wave and shock wave. So our sound wave is basically weak wave. Okay, so because it cannot do any harmful thing to our eardrums. Okay, so here, so we have assumed that this is a piston cylinder arrangement. Okay, and because here we are going to state the compressibility effect, so we just simply apply some velocity to the piston. Okay, over there. Okay, so simply we can say that I am applying the velocity dv, which is a very small velocity, and due to this very small velocity, for example, the piston is at point A, okay, for the initial stage, and when I apply some dv velocity, so the piston will move towards point number B. Okay, so from here I can say that our dv is equal to dx by dt, and due to the applying of this velocity, okay, to the piston, okay, so my piston will move to point number B and it moves the distance dv dt. Okay, so very small distance. Okay, so which come from this equation. Okay, so it's mean now the compression happen. Okay, because we are going to compress the fluid. Okay, which is inside the piston cylinder arrangement. Okay, so now here we assume that there is some wave, okay, because due to the compression, the wave are developed, and we say that this wave is moving with the speed, okay, and that speed is called speed of sound, okay, because this is, we already talked to in the previous uh, slide that our basically sound is basically a form of wave, and it is a weak wave. Okay, so we simply say that when we apply the compression to the fluid, okay, so there is the development of one wave inside the cylinder, okay, and that wave is moving with the velocity c initially. Okay, so here we can say that the velocity c is equal to L over dt. Okay, so this is an important point. Okay, and then we can also say that after compression, when the piston is at point number B, so the total distance remaining after compression will become L minus dv dt. Okay, so simply you have to minus the total length with the dv dt, which is dx. Okay, so these are some important things. Okay, so now here, okay, so here we can also say that because we are saying that our wave is moving. Okay, so for the wave we can just select one control volume. Okay, so for example, I just put the control volume and I will represent this is my wave, okay, which is developed inside the cylinder. Okay, and I assume that this is the control volume, and in order to further analyze that how to calculate the speed of sound by using this. So this is the wave, and initially this wave is moving with the velocity c and the density is rho. Okay, so after compression, okay, so the after compression the pressure become, so because if you already know that if you are going to compress some fluid, so it's mean there will be the pressure increase. Okay, so P plus dP. So this is my final pressure after compression, P plus dP. Similarly, the density is also changed because we are going to assume that it's a compressible. So we can say that it will be rho plus d rho, okay, which is our final density over there. Okay, and also if we can denote with the velocity, so our final velocity is basically at this point is C minus dV. Okay, so this we will look at how we can get this C minus dV. Also by your basic understanding from the mechanics courses, so you can easily say that because the relative velocity, so C minus dV. Also we will see in the coming lecture that how the C minus dV come from. Okay, so this is our starting point. So what you have to do is, first you have to apply the mass balance for this control volume. Okay, so first stage is to apply the mass conservation formula. So mass conservation, and you have to apply in the x direction because we are going to assume only one direction over there. Okay, so here we can say mass initial is equal to mass final. So what is the mass initial? So mass initial is basically, you already know that mass is rho into V, density into volume, and here I can say the mass initial is rho into length of the cylinder, okay, into area, okay, and the mass final is rho plus d rho, which is my final velocity after compression, final density after compression, and then length after compression is L minus dV dt. So this come from this point, and then area remains same because area there will be no effect after compression or before compression. Okay, so here I can simply take out this A because it will be cancelled. Okay, so from here C is equal to L by dt. So I can simply put the value of L as C dt in this equation. Okay, so here I can say rho into C dt is equal to rho plus d rho, and the value of L is C dt minus dV dt. Okay, so this is my one form of equation after putting the value of L. Okay, so here I can simply take out the value of dt because if I can take common, so dt can be eliminated from this whole equation. Okay, and then if I can say further solve it, so it will be rho into C, rho plus d rho, C minus dV. Okay, so here if you can notice that our final velocity after compression is C minus dV. Okay, so which I wrote over there that how this velocity come from, that C minus dV is the final velocity after compression. Okay, so from here if we can solve it further, so this equation becomes rho C is equal to rho C minus rho dV minus C d rho minus dV d rho. Okay, so from here I can simply take out this rho C because it can be cancelled, and the value of this is 0 because we already said that change in velocity is very small and change in density is also very small, and if two small things multiply together, it will result in more smaller thing. Okay, so that's why we just assume that the velocity and the value of dV into d rho is 0. Okay, and then here we can develop one equation which is rho dV is equal to C d rho. Okay, so you have to note it down this relation which we will use further in the coming slide. Okay, so this is equation number 1. So you have to note it down this point, then we will move towards the next part. If you have any question, you can also ask. simply you have to correlate with this figure. Okay, so these figures come from your book chapter, so chapter number 17. Okay, the same thing, we have assumption of the control volume over there. Okay, so now we are going to apply the second stage, which is the momentum conservation equation. Momentum conservation. Okay. So momentum conservation, you know that net force is equal to m dot mass flow into final velocity minus initial velocity. So this is the basic momentum conservation equation. Okay, so from here, if I can say, you have to find F net for on this controlled volume. Okay, so which is assumed in this figure. Okay, so how you have to calculate? So from the basic mechanics understanding, you already noticed that if there is a fluid and we are adding some and that is moving with the velocity. Okay, because this is the pressure, this is the wave, and it is moving with the some velocity. Okay, so it's mean there will be some pressure which is acting upon it, and that pressure will act from the both side of this control volume. So the P is applying on the right side as well, and P is applying on the left side as well on this control volume. Okay, so from this I can simply find the F net. So F net, the initial force is P into area, and then the final is P plus dP. Okay, because we already said that after compression the pressure become P plus dP and the area will be C. Okay, so this is the F net which is acting on the control volume, and then the mass flow is rho into area into C, which is the speed of sound, because the wave is traveling with the speed of sound over there. And then final velocity, we already see in the previous slide that this is C minus dV. Okay, C minus dV is the final velocity and initial velocity is C. Okay, so by using this relation, first thing is we can eliminate this C from here. Okay, and then we can also eliminate this P. Okay, and then we will get the final equation, which is minus dP into area is equal to rho A C D V. Okay, and area can also be taken out from this equation. So the final equation becomes rho dV. Okay, and there is minus sign also, and minus sign can be cancelled, and d rho by C. Okay, so this is the equation, and you can just denote with the equation number 2. So now what you have to do is you have to put the value from equation number 2 to equation number 1. So equation number 1 is basically rho dV is equal to C d rho. This is our equation number 1. Oh, sorry, this is dP. This is not a d rho. Okay, simply you have to put the value from equation number 1 to equation number 2, and our final equation become C d rho is equal to dP by C. Okay, and from here I can say that dP by d rho is equal to C square, and C is equal to under root dP by d rho. Okay, you can say this is for isotropic condition, because we are assuming this is an insulated cylinder, so Q is equal to 0, and then for insulated there is no heat transfer, so adiabatic, and then we can say this is the isentropic process. Okay, and then you can say this is equation number 3. Okay, and then this equation we will use for the further analysis. Okay, so till this point, if you have any question, you can ask, and then we'll move with the next one. Okay, so this is the equation. Okay, so now we have to find the value of dp by d rho. Okay, so dp by d rho value come from the simple equation for the isotropic process. So you already know T into specific volume, specific heat ratio, power specific heat ratio is equal to constant. So this is the relation which is already you are already familiar from the previous section. So from here I can simply say T by rho into K because specific volume is inverse of density and which is equal to constant. Okay, so now by applying the differentiation on both of the sides, okay, so you can say this is equation number 4 and this is equation number 5. So you have to just do the differentiation of equation number 5 and your final results will be dp by d rho is equal to k into p by rho. Okay, the differentiation you can apply by yourself because it's a mathematical knowledge. Okay, so you can easily figure it out that after differentiation, this is your end result. Okay, so now here I can put the value of P in this equation. So dP by d rho is equal to K. P value is basically rho RT. So which we already discussed in the previous slide of the thermodynamics review. So rho divided by rho. So rho is eliminated and so value of dP by d rho become KRT. Okay, so now you have to put the value of dP by d rho into this equation which is KRT. So in the equation number 4. Okay, so this is the final equation after putting the value of dP by d rho from equation number 6 to equation number 4. Okay, so KRT. Okay, so now here the proof is completed that how we have to correlate speed of sound with the different parameters of the fluid. So here is the K is the specific heat ratio coefficient, R is the gas constant, T is the temperature for the specific quantity. So if you have any question, you can ask me, and you have to note it down, and then we will move to the next part. Okay, so at this point we will stop and we'll continue with the next lecture the coming week. So if you have any question, you can ask me, and then we will just stop at this point.